If you're a super smarty pants, you might have heard the word cryptography before. Cryptography is a way to keep your information secure. It does this by using these things called keys to encrypt and decrypt your data. Encrypting is kind of like scrambling up your data so that those hooligans on the internet can't read it. Decrypting is just unscrambling your data so that the person who's supposed to see it can read it. The most secure types of cryptography use sets of public keys and private keys. Public keys are keys that are public and available for anyone to see, even the hooligans. Private keys, on the other hand, are keys that are kept secret and away from prying eyes. I won't go into too much detail about when and how to use them, but just know that data encrypted with a public key can only be decrypted with its corresponding private key, and vice versa. This means that you want the private key to be hard to guess, so that even if someone knows the public key in the encrypted message, they won't be able to guess the private key that decrypts it. Anyway, now that you know the basics, I'm going to talk about a specific type of cryptography: elliptic curve cryptography. I don't know if you know what an elliptic curve is, so here are some pictures. Whoa. Don't pay too much attention to those fancy equations. All you have to do is follow along with your eyeballs. While you're doing that, I think it's time for a scenario. Let's say we have a point with a value of a, and we want to add that point to itself. On an elliptic curve, you would do this by taking the tangent, a line that only intersects the curve at one point, instead of something like this, going to the point where the tangent and curve intersect, and flipping it over the x-axis. Since we got the new point by adding the first point to itself, the new point has a value of 2a. If you have 2 points on the curve, you can also add them together. You do this by drawing a line through the points, finding another place where the line intersects the curve, and flipping it over the x-axis. Since we added points with the values of a and 2a, the new point would have a value of 3a. From there, you can just keep adding and doubling point values to get even more points. The curve can also wrap around the graph, and after a few hours of point adding, you might get something that looks like this. Why does that matter? Well, if I knew the starting point and chose another point at random, it would be very hard for me to tell how many times the first point's value was added to get to that spot. This information would be perfect for a private key, since it's supposed to be very hard to guess, even if some information is known. Let's do another example, shall we? In this extremely simplified example, you have a super important message that you want to give to your friend, but you don't want those internet hooligans to read it. Luckily, your friend gives out a public key for anyone to use and keeps a private key to themselves. The public key contains information about the starting and ending points, which represent the letters in your message. Let's say the starting point has a value of a, and after a few additions, it has a value of b. This data will help encrypt the message, and it doesn't give away a lot of information. There's nothing that tells the hooligans how to change the letters, so if they were only given the ending point, they wouldn't be able to find the starting point at all. Now, let's say you encrypt the message with the public key and make it public. In this case, the letters of your encrypted message are like different ending points on the curve. Just like before though, the hooligans don't know how to change the letters back to see the real message. Your friend with the private key, meanwhile, can use their private key to decrypt the message. The private key includes information about how to change the letters, so it also knows how to change them back. Well, that's it I guess. Thanks for watching. I hope you enjoyed the video.